We're talking about angle measure. So an angle consists of two rays, R1 and R2, with a common vertex of O. Angles begin at the initial side and terminate at the terminal side. So the initial side is right here in each case. So think about your unit circle. It's always going to be that x-axis right there on this side of the origin. So the initial side, it goes up to the terminal side, or it will go down to the terminal side. This would be a positive angle. This is a negative angle. So it's just like what we were doing on our unit circle, where if we had a positive t, we're going to go this way. If we have a negative t, we're going to go down this way. Same kind of concept happening there. So the measure of an angle is the amount of rotation about the vertex required to move the first ray onto the second one. So this is how much the angle opens. So it's from here, moving it up to there, or from here and moving it down to there. So how much it opens. So the degree, there's a total of 360 degrees in a complete revolution of a circle. And for radians, which is the more natural method used in calculus, a total of 2 pi in a complete revolution of a circle, which is the same as our circumference of our unit circle. So to the radian measure, if a circle radius of 1 is drawn from the vertex at an angle at its center, then the measure of the angle in radians, abbreviated as rad, is the length of the arc that subtends. So I had to look up subtend, so not everybody just knows that, but that means it's the opposite from the angle. So that is the length of the arc over here. It's the arc that's opposite of an angle. And you can see some different measures here. So this is 1 radian, and then this would be like 1 radian. And then this would be pi rads, so pi radians. This would be pi over 2 radians, and this would be 2 radians. Just so you get an idea of what a radian is. All right, so here we have some relationships between degrees and radians. So 180 degrees equals pi radians, and 1 radian is equal to 180 degrees over pi. 1 degree is equal to pi over 180 radians. So if we divide both sides by pi, we end up with radian is equal to this. If we divide both sides by 180, we get 1 degree is equal to pi over 180. So as long as you understand on your circle that 180 degrees is equal to our 180 degrees is equal to pi. Trying to get my circle here. All right, so we have 180 degrees goes this way, and that's the same thing as pi. So if you get the relationship between those, you just could divide by either side. So to convert degrees to radians, you want to multiply by pi over 180, and to convert radians to degrees, multiply by 180 over pi. So think about if you're converting degrees to radians, you have to, if you had degrees over here, you've got to divide by degrees so that they cancel and you're left with pi's. If you're trying to get from radians to degrees, the degrees has to be up on the top so that you can cancel out your radian part and keep the pi. The measure of theta is equal to 1 rad, and so that's the same as 57.296 degrees. We have some degrees and radian measures. So these are the common ones, again, on our unit circle. So you can see how those relate. Notice that as it jumps, this is a little bit wider, so it's 2 of them. So that's 15 plus 15 will get you 30. Plus 15 is 45, plus 15 is 60, plus again 2 15s, get you adding 30 to that to get 90, and it continues around. So if you get, again, the more understanding of that unit circle, the better off you're going to be. Because then you're not like, what? All right, so let's go do some conversions here. So we want to express 60 degrees in radians. Move this up a little bit. So if we have 60 degrees, that would be equal to 60 degrees times our pi over 180 degrees. So remember, that way we can cancel out the degrees because they're on top and on bottom. So that gets us 60 pi over 180. These both reduce by 60. So they'll get us pi over 3 radians. All right, let's do 36 degrees. 36 degrees times pi over 180 degrees. The degrees can cancel, and you don't necessarily have to show that part, but I'm trying to get you to see the concept of how we can cancel that out. We get 36 pi over 180. They both divide by 36. We get pi over 5 radians. Now we're going to go the other way. So let's express pi over 6 radians in degrees. So pi over 6 radians would be equal to our pi over 6 times 180 over pi. Remember, that's a degree up there. Our pi's will cancel. We're equal to 180 divided by 6, which will be 30 degrees. Okay, let's do one more. So 3 pi over 4 radians would be equal to 3 pi over 4 times 180 over pi. The pi's will cancel. We have 3 times 180 divided by 4, which is 540 divided by 4, which will get us 135 degrees. All right, so the next thing we want to talk about are angles in standard position. So an angle is in standard position if it's drawn in the xy plane with its vertex at the origin and its initial side on the positive x-axis. So the initial side, so let's read that again. If it's drawn in the xy plane with the vertex at the origin and its initial side on the positive x-axis, that's standard position. No matter where the angle goes, that is the standard position of how it's going to be. Now, we have, this would be a right angle, a straight angle, an acute angle, and an obtuse angle. The way that I remember the difference between acute and obtuse, think about this is such a cute little angle, so he's acute, and then the obtuse is going to be a bigger angle than the cute little angle. All right. And acute angles are going to be between 0 and 90, and the obtuse will be between 90 and 180. So we have coterminal angles. Coterminal, remember we've talked about terminal points where they terminate. So coterminal angles are two angles in standard position that are coterminal if their sides coincide. That means they coterminate. They terminate at the same spot. So if I have an angle that goes this way and lands here, it is coterminal with one that lands coming this way. So here we could have a degree of 60, and then we can have this 420 degree angle. They are coterminal because they stop at the same point. And it can go a small one here and go around a couple of times. They are still going to be coterminal angles. We also have something that's complementary, where the two angles are complementary if they add up to be 90 degrees in total, and they are supplementary if they are adding up to be 180. All right, so let's go find some coterminal angles. So if I have theta is equal to 30 degrees, I want to find two positive coterminal angles. So I have 30 degrees. How do I get it to stop there again? Well, on my circle, if I'm at 30 and I want to land here again, I have to go all the way around the circle. All the way around the circle is 30 degrees. So if I add, it's 360 degrees to get back to our 30 degrees again. That'll get us 390 degrees. A second one, I can go twice around. Well, 2 times around, or 2 times 360, gets us 720 degrees. And if I add that to my original 30, I end up with 750 degrees. So that's how I can find two positive coterminal angles. Now let's find two negative coterminal angles. So 30 degrees, if I want negative, that means I have to go the opposite way. If I want a negative angle, I've got to go down this way. So I'm going to subtract 360 this time. So 30 minus 360 degrees will get us a negative 330 degrees. And then I'm going to do the same thing like I did last time and take 30 degrees and minus 720 degrees this time. And that'll get me negative 690 degrees. So I have found two angles that are coterminal with my original 30-degree angle. So that means they're all going to stop at that same point. So let's go find some that are pi's. So we're going to do the same process we just did, but this time our angle for theta is pi over 3, and we're in standard position. So to find two positives, to go all the way around the circle, we're going to go 2 pi. So we'll have pi over 3 plus 2 pi. Well, we have to get this to a common denominator. So we have pi over 3, so we need to find 2 pi over 3. This is 2 pi over 1. 1 times 3 gets us 3, so 2 times 3 will also get us, it'll get us 6 pi over 3. So we just multiply the denominator and the numerator by 3. Well, when I add those, I end up with 7 pi over 3. Let's do this again. So pi over 3, this time it'll be 4 pi because that's twice around. So pi over 3, and I need it over 3 again. 3 times 4 will get me 12 pi, and if I reduce those down, I still get back to 4 pi, and I get back to 2 pi. Well, this will give me 13 pi over 3. Now I want two negative angles. So I'm going to subtract. I have pi over 3 minus 2 pi. It gets easier with the negatives because we already know what it looks like. So this would be pi over 3 minus 6 pi over 3. It'll get us negative 5 pi over 3. And then pi over 3 minus 4 pi would get us pi over 3 minus 12 pi over 3 gets us a negative 11 pi over 3. So once you find what those conversion angles look like, now it's a little bit easier to do what we're looking at. All right, so our next part is looking at the length of a circular arc. So in a circle of radius r, the length of S of an arc that subtends, remember that's opposite, of a central angle of theta radians is S is equal to r theta. Solving for theta, we get theta is equal to S over r. So all we did was divide by r on both sides. This formula allows us to define radian measure using a circle of any radius r. The radian measure of an angle, theta, is S divided by r, where S is the length of the circular arc that is subtends or is opposite of theta in a circle of radius r. The radian measure of theta is the number of radiuses that can fit in the arc that subtends theta, hence the term radians. So this is basically what we were looking at earlier, what 1 radian, 2 radians, so how many radians does it take? So the area of a circular sector in a circle of radius r, the area, which is A of a sector with a central angle of theta radians, is going to be A is equal to 1/2 r squared theta. All right. So we are looking as well at, we want to find the area of a sector of a circle. Oh, there we go. So we want to find the length of an arc. Sorry about that. You want to find the length of an arc of a circle with a radius that is 10 meters that subtends, remember that just means it's opposite, a central angle of 30 degrees. Alrighty. So we know that 30 degrees, we need to put this in radians, and on our unit circle, 30 degrees is going to be pi over 6. Because we're working with something that told us that it was in radians. So we have to change this to pi over 6 radians. With our formula as S is equal to r theta, so S would be equal to, our r is 10, so it'll be 10 times our theta of pi over 6. So that'll get us 10 pi over 6. Reducing it both by 2, we get 5 pi over 3. And this is, it was in meters, so it will be meters. All right. The next thing we're going to look at is a central angle theta. So a central angle of theta in a circle of radius 4 meters is subtended or opposite of by an arc of length of 6 meters. We want to find the measurement of theta in radians. All right, so we have a couple of things here that were measurements. We had radius of 4 and we have an arc length of 6. So remember, we still have our formula, S is equal to r theta. They want us to find theta, so we're going to divide by r so that we get theta is equal to S divided by r. Well, our S, that is the length of the arc, is 6 divided by the radius of 4. That'll get us 3 over 2. and that'll be in radians. Now, if they also wanted us to find it in degrees, we could also do that. If we want to find this in degrees, that's radians, we can use the skills we've already learned. So we could say theta is equal to 3 over 2, and we'd multiply by the 180 divided by pi. So 3 times 180 would get us 540 divided by 2 pi. And you won't leave it in pi because we're doing degrees. So just divide by 2 pi. Use the pi on your calculator. 85.9 degrees. So we can still use some of the other skills that we've been learning. All right, let's go do another one. So we want to find the arc of a sector of a circle with a central angle of 60 degrees and the radius is 3 meters. So we're looking to find that arc. So we are looking at needing to change this again to radians. We have the 60 degrees and we have our radius. So remember that 60 degrees is equal to pi over 180. Oops, sorry. Is equal to 60 degrees times our pi over 180. So that gets us 60 pi over 180. You can reduce earlier if you want to. Oh, you got to be able to see the whole problem, huh? And 60 goes into 180 3 times, so we'll get pi over 3. Now for this one, we are using our formula of A is equal to 1/2 r squared theta. So we have 1/2, our r was 3, so 3 squared. Our theta is pi over 3. Well, the nice part about these is we can do a little bit of reducing if we wish, or we can just keep on going along. So 3 squared would get us 9 pi, and 2 times 3, because remember this could be over 1, would get us 6. So that'll get us 3 pi over 2, because we can divide both by 3. And these were both in, our radius was in meters, so this will be meters squared. All right, so the next thing we're going to look at is some linear speed and angular speed. So suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. I realized when I wrote this should have been area. I think I wrote arc. The area of a sector of a circle, because that's what we were doing. So sorry. It's so easy to make little oopsies. This is why we give partial credit. All right, so suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. Let s equal to r theta be the distance the point travels in time t. The speed of the object is given by angular speed. So we've got, I believe this is omega, is equal to theta over t, and here our linear speed is, looks like v is equal to s over t. So linear speed is the rate at which the distance traveled is changing. So it's going to be the distance traveled divided by the time elapsed is equal to your s over t. So this is just explaining more of what that means. So your travel distance divided by the time is what you're looking at. The angular speed is the rate at which the central angle theta is changing. So here we have the number of radians. I think that's spelled wrong. The angle changes divided by the time elapsed. So that's going to be your theta divided by the t. Notice that the angular speed doesn't depend on the radius of the circle, but only on the angle. However, if we know the angular speed and the radius, we can find the linear speed as follows. So if you know those things, and v is equal to s over t, we know from earlier, oh, here it is right here, s is equal to r theta. So we can substitute r theta over t and get r times theta over t, which is just our r times r, I believe that's omega. It doesn't really matter. It matters, but not to the point of what we're doing. So it's basically the r times our angular speed. So the relationship between the linear and angular speed, if a point moves along a circle of radius r with angular speed, then its linear speed is given by v is equal to r times our angular speed. So here's some problems we're going to look at. So it's hard to see, but this little guy here, he has a stone, and he's got it on a sling, and he's spinning around his head in a circle. It's going round and around and around. So the boy rotates a stone in a 3-foot long sling at the rate of 15 revolutions every 10 seconds. We want to find the angular and linear velocity of the stone. All right, so let's look at some of the things we know. We know it's a 3-foot long sling, so that's the measure there. He's gone 15 revolutions every 10 seconds. All righty. So that means that in 10 seconds, the angle theta changes by 15 revolutions, and a revolution is 2 pi. It's just getting us 30 pi in radians. So our angular speed which is our omega is equal to theta divided by t. Our theta is 30 pi radians. The time elapsed was 10 seconds, because we have that right there. So this will get us 3 pi, because 30 divided by 10 would get us 3 pi radians per second. Now the distance traveled by the stone in 10 seconds is going to be, that distance is equal to 15 times 2 pi r. So we have 15, because there are 15 revolutions, times 2 pi, and our radius was 3, because that is the 3-foot long sling that he had. If we multiply that, we get 90 pi feet. So now that we have the distance, we can find the linear speed. So the linear speed, remember that's v is equal to s over t, which was the distance traveled divided by the time elapsed. So the distance he traveled, or the stone traveled, was 90 pi feet divided by 10 seconds. Well, 90 divided by 10 would get us 9 pi feet per second. So that's how we're going to work something like that. So let's go find the linear speed from the angular speed. So we got a woman, she's riding a bicycle, whose wheels are 26 inches in diameter. If the wheels rotate at 125 revolutions per minute, RPMs, find the speed at which she is traveling in miles per hour. we're going to be doing some conversions here. All right. So first we're going to find our angular speed of the wheel. So the circumference would be 2 pi, and we were told that it rotates at 125 RPM in 1 minute. So revolutions per minute. So that's 250 pi radians per minute. Now the wheel radius, we've got to find the wheel radius. They gave us the diameter, and the radius is going to be half of the diameter. The diameter was 26 inches, divided by 2 will get us 13 inches. So now we can find our linear speed, which is our V equals R times W, or our omega, sorry about that, looks like a W. So our R is 13, and our angular speed is going to be 250 pi. Well, that gets us 10,210.2 inches per minute. But we need miles per hour, so we've got to do some dimensional analysis here. So we'll take 10.2 inches per 1 minute, and we've got to go inches to miles, so I can do inches in a foot, so 12 inches is equal to 1 foot. And I happen to know there's 5,280 feet in a mile because I know it's 5 tomatoes. It's something I learned from one of my students. So 5280, 5 tomatoes. He learned it from a teacher, so I did not come up with it, in 1 mile. So the feet cancel and the inches cancel, and we've got our miles. Now we need to get to hours. All right, so in 1 minute, I need to get rid of my minutes. So I have 60 minutes in 1 hour. So my minutes are now canceled, and I have it to an hour. So if I multiply across, I get 10210.2 times 60. That'll get us 612 miles on the top, divided by 12 times 5280 would get us 63360 hours, and that will get us 9.7 miles per hour. So make sure you do all of your increments and that they cancel, so you make sure you're getting to your right value.